Okay, let us start. So we see that by looking at the closed loop pole locations, we can actually try to understand which system is more stable. If the closed loop poles of a system are further away from the imaginary axis than the closed loop poles of another system, then we would say that the one closed loop system is actually more stable than the other one. But in these Nyquist plots and the border plots, we would like to be able to do this thing based on the frequency domain representations of the system. So frequency response of the system. That is actually what we are going to do in this lecture. So here, if we have a closed loop system given in the following form, I have G of S and H of S in the in the feedback path, then in this part we are going to have some mild assumptions here. So these assumptions are going to be the following. The first assumption is that all zeros and poles of G of S, H of S have non-positive real parts. Real parts. Okay, this is our first assumption. And the second assumption is limit as omega goes to infinity, G of S, H of S, S equals to J omega goes to 0. Okay? In some way we are assuming that all zeros and poles of the G of S, H of S will be non-positive, and we are assuming that there are more poles than zeros. Okay, so this term is given like that. So in some way you can actually try to understand what these requirements are. In some way, what we would like to do is that when I give a sinusoid to a system, I want the response to be bounded. Okay, so I don't really want terms which are making the frequency response infinite anywhere. Okay, so here this type of assumption would ensure that when we give a sinusoid to the system, not all sinusoids, but for some sinusoids, the response of the open loop system is going to be finite, and this is a physical system restriction somehow. All physical systems would behave like low pass filters. Okay, so when you increase the frequency, those amplitudes the system would always attenuate high frequencies. So here we are going to use two frequency domain measure for stability. So the first measure is going to be called gain margin, and the second measure is going to be called phase margin. This is GM and this is PM. Okay? And in this case, we are going to be asking how stable, if a closed loop system is stable, we are going to ask the question, how stable is the closed loop system? So I would like to give a number. I would like to quantify the amount of stability for the system. And I'm going to quantify that stability based on gain margin and phase margin. I will tell you these numbers. So now let us start with the gain margin definition. Gain margin is the factor by which the open loop gain can be increased before the closed loop system becomes unstable. The higher the gain margin is, the more stable the closed loop system is. The gain margin in dB scale has to be, yani her şey yetmiyormuş gibi bir de dB scale'e geçmemiz gerekiyor. Has to be positive for a system, for a closed loop system to be stable. Okay. And now I'm going to spend some time explaining this definition. So suppose that I have my system given like this. So here is my system. 1 over s plus 1, s plus 2. Okay? This is my system. In general, I'm going to have the following. I'm going to have this picture. Okay? This is the general picture. But here h is 1, and I'm given this system. So here I can actually try to draw a root locus for this system. And here in this case I see that k is equal to, so here if I consider a gain, then that gain is k is equal to 1. Okay? So now I can try to determine whether such a system is stable or not. I can calculate the closed loop transfer function. G closed loop of s is going to be 1 over, I will have s cubed plus 3s squared plus 2s plus 1. Okay? So this is my system. And when I look at the closed loop pole locations, the roots of this polynomial are at minus 2.32 and minus 0.33 plus minus 0.56j. So if I look at the closed loop pole locations for such a system, then they're going to be located at such points. There is going to be at minus 232, and there will be some complex poles here at these locations. Okay? Do you think this closed loop system is stable? It is stable, right? So in this case, because all of the closed loop poles are in the open left half plane, so the closed loop system in this case is stable. Now the question is, how can I quantify the stability of such a system? We are going to be able to quantify it by using the gain margin. And the gain margin is going to be showing us the factor by which the open loop gain can be increased before the closed loop system becomes unstable. So here is what I'm going to do. I'm going to take this system, that is my original system, and I will create a hypothetical system here. This is a system non-existent. I will put here a k value, okay? So here I will have 1 over s plus 1, s plus 2. Okay? This is my hypothetical system for measuring the gain margin. Okay? The original system corresponds to the k value 1. Okay? This is my original system, and this is my hypothetical system. And we see that the original system corresponds to a special case of the hypothetical system. Okay? And I know that k original is 1. Okay? When I set k is equal to 1, I get my original system here. Okay? Now the question is, how much can I increase this k above its original value such that the closed loop system start becoming unstable? Okay? I will increase the k value from the original value 1, and then I will look at which k value the closed loop system is unstable. So this k is called the open loop gain somehow. Okay? I will increase this open loop gain until the closed loop system becomes unstable. Then that specific k value divided by this k original is going to be my gain margin in linear scale. And the larger that value is, the more stable that I'm going to call my system. Okay? So here, let us try to find that k value. So when I place this k here in this loop, then I turn my characteristic polynomial into the following: s cubed plus 3s squared plus 2s plus k is equal to 0. This is the characteristic equation of the hypothetical system. That is the closed loop denominator. in my hypothetical system. Okay, and when I apply, for example, route stability criterion to this s cube, s square, I have 1, 2 here, 3, and k. So I have s, and I have 6 minus k divided by 3, and I have k here. Okay, so we see that k should be between 0, 0, and 6 for stability. Okay, and when I look at the root locus of the same system, I see that there are open loop poles at these locations, and if I complete this root locus into a full one, I would see something like this. Okay, what do you think this point is? Which k value does this point correspond to? K is equal to 6. So this is the point at k is equal to 6 here. Okay. And here I can actually try to find also what the intersection value of this. What is this point in complex plane?
Plus minus square root J2.
Yes. How do you know?
S square polynomial.
Yes. I go one row up. This is the second type of difficulty. Okay. So I have the auxiliary polynomial is p of s is equal to 3s squared plus k is equal to 6. Okay, it is given like this. So the solution of this thing, or roots of this thing, are at plus minus j square root 2. Okay, but here I have plus j square root 2, and here I have minus j square root 2. Okay, so we see that at k is equal to 6, the closed loop system becomes unstable. At k is equal to 1, this is my closed loop pole locations. So we see that at k is equal to 1, one of the poles is closed loop poles is here, and the other two are somewhere here. Okay? And when I increase k to the value 6, we hit the stability boundary. Okay? Then I'm going to define the gain margin of the system as k unstable divided by k original. This is the gain margin in linear scale. Okay? And in this case, k unstable is 6, k original is 1 here. That means that gain margin of the system is 6 in linear scale.
Hocam?
Yes.
How can you find k original? Like, is that the direct DC gain of the system?
Actually, here I might have 2 as well. Okay, it really doesn't matter. As long as I can put here 2, then k original is always going to be 1 actually. Okay, if you place this system given here into here directly, whatever the DC gain of the original system is, k original is always going to be 1 in that calculation. Okay. So here we see that this is our gain margin. Okay, and it is in linear scale. If I would like to convert it in dB scale, what should I do? 20 log 10, and I have 6. Okay, this is 20 log 2 plus 20 log 3. When I don't write anything here, in this course we most of the time we don't use logarithm other than the logarithm base 10. Okay, so here, if I don't write any base for the logarithm, you need to assume that it is base 10. What is log 2? What is this? Take the logarithm. What is the logarithm of this thing? It is 10 log 2. Okay. What is the log 10 of this thing? What is log 3? Take the logarithm. Okay? is the log of this thing? Take the logarithm. Okay. So here we see that this is approximately 0.3 and this is approximately 0.5. So it is approximately 16 dB. Okay. So that is our gain margin in dB scale. But as I told you, this is not our aim in this part of the course. Obviously, we would like to find the gain margin, but we would like to be able to do this in frequency domain quantities. We would like to be able to do the same thing in actually body plots and in Nyquist plots. Okay. So here I will try to show you the main idea here. When you take this system, then if you try to draw its body plot, it's one of our examples. Okay, we have already drawn the Nyquist plot of this same system. Okay, and it is looking like this. So I have this thing here, n over d, an imaginary n over d here. It starts at infinity, and this is the part which is at infinity for this Nyquist plot. And it goes from here, and then it passes somewhere like this, and it passes from this. Okay. This was the Nyquist plot for the same system. And we have actually found this point as minus 1 over 6. Okay? And this point was at infinity. Okay? So when I have something like this, then there is some specific part of a Nyquist plot that is called the polar plot. Polar plot is the following part of the Nyquist plot. Okay? This part is nothing but the part of the Nyquist plot that we draw for the positive imaginary axis. Remember our Nyquist path for this example. For this example, the open loop poles are at -1 and -2, and we have obtained the Nyquist path given like this. I have the point A, I have the point B, and point C, and point D here. The part from B to C that we draw for the Nyquist plot corresponds to the frequency response of the open loop system. Frequency response of that system, this system, which is the open loop system. Okay? The part from B to C here, in this Nyquist path, corresponds to part from B to C here in the Nyquist plot. Okay? This part is called the polar plot of the system. Okay? And this part is going to be the part of the Nyquist plot which we are going to convert into a body plot. It is not really difficult to draw this polar plot without making any analysis at all. So here, let us try to understand what happens in this polar plot. So I have 1 over, I will pass this thing into frequency domain. I have 1 over j omega, 1 plus j omega, and 2 plus j omega. Okay? This is my open loop system. And suppose that I would like to plot the polar plot of this system into the complex plane. Okay? I know that in this part, S is equal to j omega, and omega changes from epsilon to infinity. Okay? Omega changes from epsilon to infinity. Now, if you look at this quantity, what happens to the magnitude as omega goes to 0? What happens to the magnitude of this thing as omega goes to 0? It blows up, it goes to infinity. If you look at this thing, as S goes to 0, because there is a pole at S equals to 0, magnitude diverges to infinity. What happens to the phase of this quantity as what happens to the phase as omega goes to 0? İlk başta zor gelecek. Tamam mı? Yani ilk başta anlaşılmayabilir. Ama şuna bakınca şunu nasıl çizeceğiniz çok basit. Tamam? So don't get intimidated. This is not something difficult. So if I let omega go to 0, when I let omega go to 0, this thing is just going to behave like 2, because j omega is going to be negligible. This thing is going to be just 1. Omega is negligible when omega is 0. And as omega goes to 0, this is going to just behave like 1 over j omega. Okay? What is the magnitude of 1 over j omega as omega goes to infinity, or omega goes to 0? It goes to infinity. It belongs to infinity. What is the phase of 1 over j omega as omega goes to 0? Minus 90. So the polar plot is going to be here at omega is equal to 0. As I increase omega, these terms will start bringing additional phase lag to me. So these are going to rotate. But what is going to be important for me is that what happens as omega goes to infinity. If omega is very large, then this term is going to behave like j omega. This term is going to behave like j omega. So I will have, as omega goes to infinity, I will have 1 over j omega cube. Okay? What is the magnitude of this thing as omega goes to infinity? 0. It is going to go to 0. What is the phase of this thing as omega goes to infinity? Minus 270 degrees. So I'm going to draw something like this. Okay? So here, 1 over s plus 1. So let me say something like this. I have here s squared, s plus 1. Okay? I will substitute 1 over j omega. We will just draw the polar plot of this thing. J omega squared, okay? 1 plus j omega. Okay? I would like to draw the polar plot of this thing. I will let omega go to 0. What is the magnitude? What is the phase? If I let omega go to 0, this term is going to behave like 1. But when I have 1 over j omega squared, if omega goes to 0, the magnitude is going to go to infinity. Okay? What about the phase as omega go to 0? Minus 180. So we're going to be somewhere here. Okay? And what is the phase? What is the magnitude and phase as omega goes to infinity? The magnitude is going to go to 0. Phase is going to go to minus 270. So polar plot of this thing is going to be looking like this. Minus 200 and 270. Okay? 1 over s plus 1, s plus 2.
Hocam,
Yes?
how do you know that it's not going like this way?
What do you mean?
Hocam, j omega eksi geçip oradan dönüp gelmediğini nereden biliyoruz?
It can do it. Without detailed analysis, you cannot do it. But here I'm trying to explain the beginning points and the end points. Okay? So here there might be an intersection in that, especially if it had zeros. I would have said that there would be. But here I see that the phase is always going to be decreasing. Okay? So because there is no zero, phase is always decreasing. That is why I have plotted this in that way. Okay? So here 1 over s plus 1, s plus 2. So here, why are these plots going to infinity as omega goes to 0? No. As omega goes to 0, these are going to infinity. Why are they going to infinity? Yes, poles at 0. Okay? So here, these are diverging to infinity because of these poles at 0. Okay? If there is no pole at 0, then I can say that the plot is going to be finite. Okay? If I look at this system, 1 plus j omega and 2 plus j omega, if I look at this system, if I would like to draw the polar plot, where should I plot the omega is equal to 0 case? What is going to happen at omega is equal to 0? It's just going to be 1 over 2. It's going to be here finite. Okay? And what can you say as omega goes to infinity? the magnitude is going to go to 0, the angle, phase, is going to go to minus 180 degrees. Okay? That actually means that, and here, when I look at this thing, because this thing doesn't have any 0, I can say that phase is always going to decrease here for this transfer function. Because as this omega increases, the phases of these complex quantities will increase. And because they are in the denominator, phase is always going to decrease here. That actually means that the polar plot is going to come here. So do you think we are going to go to 0 from that axis, like this? As omega goes to infinity, I will converge to 0 like this, do you think? No, I have to convert, as omega goes to infinity, the angle has to become minus 180 degrees. Okay? That actually means that here, I need to turn here and I need to go to 0 in that direction. Yes?
Üstteki örnekte 1 bölü c omega kare çarpı 1 artı c omega var ya.
1 bölü, evet.
W hem infinity'ye giderken hem sıfıra giderken ikisinde de eksi 270 derece.
W sıfıra, omega sıfıra giderken bu arkadaş reel bir sayıya dönüşüyor, 1 oluyor. Tamam mı? Dolayısıyla bu W sıfıra giderken faz getirmiyor bana. Yani omega sıfıra giderken bu terim faz getirmiyor. Omega infinity'ye giderken ama bu eksi 90 derece faz getirmesi lazım. Tamam mı? Any other questions? Okay, this is the concept of a polar plot. Okay, and when I see that it is a part of the Nyquist plot given like this. So now when you look at a Nyquist plot, if you actually identify the polar plot part, then you would actually see what is happening. If the polar plot goes to infinity, then you would know that there are poles at 0. Okay? And by looking at the angle by which we converge to 0, you can actually understand how many more poles than we have zeros. So now the question comes. I have this Nyquist plot for this system. Okay? How can I check the closed loop stability of this system? By checking the encirclements of what? So here, P for this example is 0. Okay? P is 0. Z is equal to n plus P. Since P is 0, Z is equal to n. So the encirclement, non-zero encirclement, will mean non-zero unstable closed loop pole. Okay? So as soon as the Nyquist plot encircles minus 1 over k, we will get instability in the closed loop system. What is k in this original system? K is equal to 1 in this original system. So the encirclement of which point should I check for? I need to check the encirclement of minus 1 over k, which is going to be minus 1. Okay? So what is going to be important for us for stability of such a system is that when I draw the Nyquist plot of this thing, it shouldn't encircle the point minus 1. Okay? So the encirclement of minus 1 is going to mean instability. So now another question comes. So when I add the hypothetical gain k here, okay, I put a k here, okay, that is my hypothetical system, okay. How does this Nyquist plot change when I add here, for example, k is equal to 2? If I add plus 2, if I make addition, then it's going to shift to the right by 2. But here this is multiplication by 2. Then it is going to be scaling, right? So here, if I put here the gain 2, this is going to be scaled, all right? Then I will ask you the following question. At which scaling are we going to start encircling the point minus 1? At which scaling we are going to start encircling point minus at 6? It is exactly the same thing that we are finding. And in order to be able to find that, which point should I concentrate on?
Minus
on this original Nyquist plot, yes, I'm concentrating on the encirclement of -1, but on this Nyquist plot, which point determines the number 6?
Intersection of limits.
This point determines. This is probably the most important point in that Nyquist plot. It actually determines the stability boundary of such a system. In the original system, k is equal to 1, so no encirclement of the point -1. But as I increase k, this Nyquist plot is going to be scaled up and it's going to get larger and larger. And if the gain hits k is equal to 6, we're going to start encircling the point -1. Okay? And that -1 is determined by such a point on the Nyquist plot. This part of the Nyquist plot, as I told you, is the polar plot, and it is drawn for the frequency response of the system. So frequency is 0 here. This is omega is equal to 0, and frequency is infinite here. Okay? What is the frequency? What do you think the frequency here is? Yes, that is quite magical actually. Okay, because here I have the following equation: 1 plus k, 1 over s plus 1, and s plus 2 is equal to 0. This is the closed loop equation. Okay, then I see that this equation is s plus 2, s plus 1, s plus 2 is equal to -1 over k from this equation. And I see that at k is equal to 6, this ratio at k is equal to 6, this is going to be -1 over 6. Okay? So and when you substitute j is equal to omega here, and when you try to solve that equation, you're going to end up with j square root 2. Okay? So here, at this frequency, omega is equal to square root 2 radians per second. Okay? And the gain of the system at that point is 1 over 6. Okay? Because when I take the gain of these two quantities, the gain turns out to be 1 over 6. So here, let us try to go over this thing. So here, on this Nyquist plot, what is going to be important for us is going to be such a point. This point is the point at which the frequency response of the system intersects the negative real axis. Okay? What is the property of negative real axis? How can I describe negative real axis? What is the property of these points here? The imaginary part is 0. That is one of the characteristics. But positive real axis would also have the same property. So it's not distinct. That property is not distinct to negative real axis. What is important for negative real axis? Sorry? Yes, that is positive again. So I would like to find what is actually satisfied for any of these numbers. So do you think their magnitudes are the same? Magnitude of this point is different than their magnitude of this point. Okay, so the magnitude is not determining whether a point is on the negative real axis or not. What about the phase? Yes, phase becoming equal to 180 is the describing characteristics of the negative real axis. Okay, so when I have a system given like this, so I have G here, and when I have H here, if I would like to find when the Nyquist plot of such a system, GH, would be actually intersecting the negative real axis, then what I try to solve is the following. G of j omega, H of j omega, I equate this to minus 180 degrees. Okay? If I would like to find on a polar plot, this is the frequency response of the open loop system here. if I would like to find where a polar plot intersects the negative real axis, the characterizing equation for that is this equation. I look at when the open loop system has phase minus 180 degrees. Okay? And the point, the frequency at which this equation is satisfied is called the phase crossover frequency. Okay? This is called omega p here. Okay? Omega p is called the phase crossover frequency. Okay. And how can I define it? It is the frequency at which the angle of the open loop transfer function intersects minus 180 degrees. Okay? It is the phase, it is the frequency at which the phase of the open loop system, open loop frequency response, let us say, frequency response, intersects minus 180 degrees. All right? If I know this frequency, omega, here for this example, what is that frequency? It is square root 2. Square root 2 radians per second is the phase crossover frequency of this system. Okay? And then by knowing this frequency, how can I determine the gain margin of the system? I need to look at the magnitude of the frequency response here at that point. Okay? I will obtain the magnitude 1 over 6 at that point. And from that, how can I go to the gain margin? If I have the magnitude 1 over 6, what is the gain margin? 1 over is the reciprocal of that number is going to be my gain margin. It is the magnification constant that I have to use to make the Nyquist plot encircle the point minus 1. Okay? So the gain margin of the system in linear scale is the following. It is 1 over the magnitude of the open loop frequency response at the phase crossover frequency. It is this one. So this magnitude for this example is 1 over 6. Okay? And when I divide 1 by 1 over 6, I get 6 as the linear scale phase margin. Okay? Sorry, gain margin. And in dB scale, what do I have to do for obtaining the gain margin? I just have to take 20 log of this thing. So gain margin in dB scale is going to be minus 20 log of j omega p h j omega p. Okay? That is what the gain margin is. So if you have the dB scale body plot, you will locate where the phase crosses minus 180 degrees, and you would look at the magnitude in dB scale in that case, and the negative of that value is going to be your gain margin. Okay? So here the gain margin, the linear scale value is actually 6, which is larger than 1. Okay? If the original system had the following Nyquist plot, okay? If the original system had this Nyquist plot instead, okay? So the gain in that case is larger than 1. Okay? What would happen to this gain margin in that case? If I calculated, I would find the phase crossover frequency at this frequency, and then I would find the magnitude there. Okay? The magnitude there would be larger than 1 or smaller than 1. The magnitude here. It is larger than 1. It is this distance, this magnitude. Okay? You see that at 1/6, the magnitude is smaller than 1. That is why the gain margin is larger than 1. Okay? If the magnitude is larger than 1, gain margin is going to be smaller than 1. Okay? So here, what can you say about the Nyquist plot? What can you say about a system which has a Nyquist plot in this form? It is unstable by itself. And what can you say about its gain margin in linear scale? In that case, it's going to be less than 1. Okay? So then when you look at these gain margin values in dB scale, okay? In such a case, if this magnitude is larger than 1, then I see that the gain margin is going to be negative in dB scale. Okay? Then magnitude being larger than 1 means instability. In such a case, gain margin is going to be negative. If the magnitude is smaller than 1, then gain margin is going to be positive. That is why we say that for a closed loop system to be stable, we need that gain margin in dB scale to be a positive number. Okay? We need positive gain margin in order for a system, for a closed loop system, to be stable. So let me try to define what phase margin is. We are not going to be able to work much, but I can give you the main idea. Let me write the definition of the phase margin. Phase margin is the maximum amount of phase lag one can add to the open loop system before the closed loop system becomes unstable. The higher the phase margin is, more stable the closed loop system is. And we have phase margin has to be positive for a closed loop system to be stable. Bir şey okuyamadınız mı? Remember, gain margin is related to addition of the gain into the open loop system. Okay? So here, I add a hypothetical gain into the system. Okay? So for phase margin, I really do not add a hypothetical gain anymore into the open loop system. So I have 1 over s plus 1, s plus 2 here. Okay? I have this thing. And instead of some gain, real gain there, I will add a phase lag. Okay? A phase lag is going to have the form e to the minus j phi here. Okay? It is just going to be a phase lag. Given like this. If you have a complex number, this complex number is z. Okay? This is real of z, imaginary of z. If I multiply this complex number, z, with e to the minus j phi, then what does that multiplication do?
Reduce phi amount of angles.
Yes, so is it going to change the magnitude of z? It's not going to change the magnitude of that. It is just going to change the phase. How is it going to change the phase? We are going to add minus phi to the phase. So we are going to rotate this clockwise or counterclockwise. If phi is positive, we are going to rotate this clockwise or counterclockwise. I'm going to rotate it clockwise by the angle phi. Okay? So this is going to be my z times e to the minus j phi, and this is my angle phi. Okay? The original system has phi is equal to 0. This is my original system, and it is phi is equal, it corresponds to phi is equal to 0 here. Okay? When I start adding non-zero phi, so we don't encircle the point minus 1 for the original system. So what happens when I add non-zero phi? What happens to the Nyquist plot in that case? Every point is going to be multiplied by this complex exponential. So what is going to happen to this Nyquist plot? It is going to rotate in clockwise direction. Okay? So everything is going to rotate here around to origin, and we see that because this part is infinity, at some angle phi, we are going to start encircling the point minus 1. Okay? So when this thing rotates, at some point, at some rotation angle, we are going to start encircling the point minus 1. Okay? That angle at which we reach instability is going to be called the phase margin of the system. Okay? That is our phase margin. How can I determine such point? Which point here on this polar plot is going to hit minus 1 when I rotate this? I will draw here a unit circle. Okay? An intersection of the unit circle with this polar plot is going to be the first point that is going to hit this point minus 1. Okay? Unit circle is the points on which the magnitude is equal to 1. Okay? We are going to find this frequency. It is going to be called the gain crossover frequency in this case. And its angle is going to give us the phase margin. Ama hepimiz bayağı yorgunuz. O yüzden bence faz marjını burada keselim. That's all for today. Thank you very much.
Hocam ben imza atmamıştım.
Tabii.
Şimdi şeydeki gain margins'ini bulduğumuz yerde dönem frekansı phase crossover frekansı.
Evet.
Bundaki gain
Bundaki evet öyle
biraz
karışık var.
counterintuitive değil mi?
Evet, counterintuitive.